All right, I'm recording. I'm going to share my screen and we'll go to 9.0a. All right, so can you see that? Estelle, you can
Yes,
see
I
it?
can. Sorry, my mic.
That's all right. All right, here we go. 9.0a. So we're talking about hypothesis testing this week. Hypothesis testing is basically testing out whether what you think is true is actually true. And the way they do it is they fit a situation to a particular test. You have the z-test, which uses the normal distribution. So that one you're going to use if you know the population standard deviation, you're going to use the z-test. Or if you have the single population mean problems, like in the second section, we're going to do the single population proportion. We would use the proportion z-test for that one. If you don't know the standard deviation of the population for the population mean, we use the t-test. All right, so, but that'll be pretty easy to figure out when we do the problems. So basically a hypothesis is something like this. You wish to test the following claim at a significance level of alpha equals 0.01. Okay, so the claim is the mean is 70.1, and the alternate H sub A, the alternate hypothesis is the mean is not 70.1. So you believe that a population is normally distributed and you know the population standard deviation is 10.8. You obtain a sample mean of X bar equals 74.5 for a sample size of N equals 22. Okay, so first of all, you know the population standard deviation is 10.8. So this tells us we're going to use the z-test. All right, and I believe that we're going to use the z-test for like the first four of them, first four problems. So this one we're going to use the z-test, which is under the stat test scenario. So that's what we're going to do right now. We're going to go to stat, and then we go over to tests, and you're going to see test number one is the z-test. So basically today we're going to use either 1, 2, or 5. 1, 2, or 5. I think 3 and 4 might come up in 2 weeks. All right, but we're going to use number one, the z-test. So we're going to input stats. If you're given a list of data, you would choose data, but we're given the stats already. So we know the mu0 is going to be that 70.1. And then the standard deviation is going to be 10.8. And then our X bar is going to be 74.5. So that means we collected a sample of 22, whatever. It doesn't say the scenario we're dealing with, but we took a sample of 22. That sample had a mean of 74.5. So does that disprove the mean of 70.1? Is there statistical significance that we would reject the claim that the mean is actually 70.1? All right, so we have this information. We're going to go down to either calculate or draw. If you go to draw, you're going to see that I didn't choose the right mu, did I? Yeah, I did not choose the right one. See how it says mu is not equal to 70.1? That means I want to choose that one right there, the not equals to. All right. So then if I draw that, then you should see the two tails that are covered in. And all this stuff's in my way now. All right, so the two tails, and it gives you this test statistic is 1.9109. So that kind of gives you the standard deviations away from the mean, right? The mean's the vertical bar right here, 1.9109. Those tails show the kind of the z value and the p value are they're in cahoots. The z value of 1.9109 gives you a probability of 0.056 in the tails. But that's what we're gonna write in there. We're gonna write in 1.911 because it wants it to 3 decimal places. The p-value, well, they want it to 4 decimal places. We're gonna have to find the 4th decimal place in the z-test. And instead of choosing the draw, we're gonna choose the calculate. In fact, I would just use the calculate every time. And then you got the p-value 0.0560. So then what you do with this information is you compare it to the level of significance. So the lower the level of significance, the more difficult it's going to be for our data to be out in those tails for this one. All right. So you got a 0.056. That's bigger than 0.01. So whatever the p-value is, you compare to the significance level is bigger. And if it's bigger, if the p-value is bigger, then we're going to fail to reject the null. All right, the p-value smaller, we would reject the null. So the only 2 possibilities for the answer to this one, reject the null or fail to reject the null. So the p-value is bigger than the significance level, so we're going to fail to reject it. Okay, so the final conclusion then is there's not enough evidence in this case to reject the claim that the mean is 70.1. So let's see, there's not enough evidence to warrant rejection of the claim that the mean. See, these are tricky, so I'm going to put that and see what happens. Of course, I got it wrong. Yeah. So the final conclusion, there's not, because there's not sufficient evidence. So whenever you reject the null, the words are going to start with there is not sufficient evidence. So it's going to be this one. There's not sufficient evidence to support the claim that the population mean is not equal to 70.1. All right, if that p-value is really small, then there would be sufficient evidence. Okay, so, I mean, if you watch the video, for sure, Wendy's video, these would make much more sense. All right, let's see. So I was going to skip to number 5, but would you all like to do one more of those? I'm guessing yes, right?
Sure.
So let's take a look at, let's see. 2 is kind of exactly the same. Let's look at 3. So the mean age when smokers first start is 13 years old. That's kind of scary. With a population standard deviation of 2 years, right there. There's your keywords right there. Population standard deviation. We know that, so therefore this is a z-test problem. You know the population standard deviation, we use the z-test. Okay, so the null hypothesis, this is called, we're talking about the population mean, so mu, and the H0 is always going to be equals in the middle. Always, 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 always equals. All right, 13 years old. And then it says a researcher thinks the smoking age has significantly changed since the invention of ENDS, electronic nicotine delivery system. A survey of smokers in this generation was done to see if the mean age has changed. The mean age has changed. That's does not equals. All right, because you're going to see 3 different inequality symbols here: less than, greater than, or does not equals. This is going to be a does not equals. 13 years. Now we go to our calculator and we do find the test statistic, which is the z value, and then we find the p value. All right, so we go to stat, test, z-test again. So we're going to input the stats. This time we're using 13. We have a population standard deviation of 2. We got it says the sample of 31 smokers found their mean starting age was 12.4. So 12.4. And the number of smokers we surveyed was 31. And then we got to choose the right does not equal, less than, or greater than. We choose the does not equal. Down to calculate. And there's our Z value is negative 1.670. That doesn't make, well, it was right. I was gonna say that doesn't make much sense, but 0.0949 is the p value. So then we're at a 1% significance level. 1% significance level. Well, 9% is way bigger than 1%. So the p value is bigger than the significance level. That means we fail to reject a null hypothesis. Smaller than, we're going to reject the null hypothesis. Bigger than, fail to reject it. Correct summary would be, there's not enough evidence, let's see, to whatever the researchers claim that the mean age of smokers is different than 13. There's not enough evidence to support the researchers' claim that the mean age is different than 13. Okay. If we rejected the null hypothesis, then there would be enough evidence to support it. All righty. So what do y'all think about that one? That good, huh? All right. So let's go on to number 5, and let's read about how number 5 differs from number 1, 2, 3, and 4, because 1, 2, 3, and 4 all operate pretty similarly. Okay, so that one does too. It kind of breaks it down a little bit different, but it's the same problem. All right, let's read 5. The average amount of time it takes for couples to further communicate with each other after their first date has ended is 2.59 days. Is this average shorter for blind dates? Okay, so right there, we can go mu equals 2.59. Is it shorter for blind dates? So shorter means less than. So mu is less than 2.59. So we're going to enter those in there, and we got them right. But let's see why we're going to choose what we choose here. It doesn't talk anything about the population standard deviation. It says we interviewed 48 couples who had recently been on blind dates and found that they averaged 2.4 days to communicate with each other after the date was over. Their standard deviation was 0.549 days. So 2.4 days is less than the 2.59 days, but can you conclude conclusively that it is, like, for the population of blind daters, is that going to be different? Is that going to be less than 2.59? So that's why we got to come up with the statistic. You're not given anything about the population standard deviation, so we're going to use the t-test. All right, the t-test works pretty similarly. So let's see, let's check it out. We go to stat, over to tests. This time we're going to choose option 2, the t-test. Hit enter. Now we're going to input stats again. We know the mu is 2.59. That's my mu sub 0, population mean. We got our mean was 2.4. Standard deviation of that sample was 0.549. And we asked how many? 48 couples we asked. Now, my mu, is it not equals, less than, or greater than? Well, it's less than. So we're going to go over there and choose the less than. Then I'm going to calculate, and we get a t statistic of negative 2.398. And then the p value is 0.0103, it looks like. So, and we want a level of significance of 0.10. Oh, good, we got a less than this time. So the p-value is less than the 0.1, the alpha. So that means, the p-value being less than that, we're gonna reject the initial hypothesis then. We're gonna reject mu is equal to 2.59. So we have statistical evidence. What they're saying is a p-value that's that much lower than the level of significance, that's pretty difficult to achieve unless the mean was actually less than. All right. So that's why we are going to reject the null hypothesis in this case. All right, the final conclusion. The data suggests that the mean is not significantly less. The data suggests the mean is significantly less. So that's the word you should be looking for. Whenever you reject the null, you got data that indicates a significant level of difference than what they came up with. And you're probably going to conclude, or you're definitely going to conclude then, that the mean time for couples who have been on a blind date with each other is, well, after the first date's over, is less than 2.59. So that's what we're going to choose there. Bing, and we got them all right. Okay, so I'm glad that we got one where the p was less than the alpha. So whenever the p-value is less than alpha, you reject the null. Therefore, the data is makes statistical significance to conclude otherwise. All right, it's very tricky. I know the concepts are very tricky. I had to read the chapter, but like I told you all before, I haven't taken prob and stat since the early 80s. So I read the book, I watch the videos, I do the homeworks like 3 times to make sure I can hopefully get it right when I explain it to you. So what questions on that one? Okay, let's see a couple more then in this one. That was number 5. Yeah, I was going to check out number 8. So 6 and 7 work the same exact way. You just go through all the steps. 8 asks a couple of, so does 7, but 7 and 8 ask a couple of additional questions at the bottom about the p-value and the level of significance. So average number of accidents at controlled intersections per year is 5.1. Is this average less for intersections with cameras installed? The 51 randomly observed intersections with camera installed had an average of 5 accidents per year. The standard deviation was 0.59. What can be concluded at the 0.01 level of significance? We do not have the population standard deviation, therefore we're doing the t-test. Our null hypothesis, mu equals 5.1. And they want to know, is the average less for intersections with cameras installed? So mu is less than 5.1. Okay, got all those. Now I go to my calculator and I input all that stuff. So stat, test, t-test, and then we want to input the stats. My mu 0 is 5.1. My X bar is 5. My standard deviation is 0.59. And I was able to do 51 random observations, and less than is what we want. So go down to calculate and we get our information. So the test statistic, T is negative 1.210. My p-value is 0.1159. That's pretty high p-value, definitely higher than the level of significance. So p-value is greater than alpha, therefore we failed to reject. That means we do not have significant evidence. All right. So you're going to look for the not significantly less than and try to figure out which one's correct. So the second one's definitely wrong. Let's see, the first one. Data suggests the population mean is not significantly less than 5.1 at alpha is equal to 0.101. So there's statistically insignificant evidence to conclude that the population mean number of accidents per year is less than 5.1. That sounds right. Let's see how it differs from the last one. The data suggests the sample mean is not significantly less than 5.1 at 0.01. So there is statistically insignificant evidence to conclude that the mean number of accidents per year. See those words. So there is less than 5. Well, let's see. I think it's, let's see. Do we get it right? No. So it's the first one because we're talking about yeah, see, I went off track here. This is what we got in the sample. What the population mean was is 5.1. That's what we're trying to prove or disprove. So we should have chosen the first one. Okay, let's see these ones. The p-value in the context of the study. The p-value is 11.59%. It's always going to be one of the paragraphs. Here's a little hint for you. It's always going to be one of these paragraph ones. So if the population mean number of accidents per year at intersections with cameras installed is 5.1, and another 51 intersections with cameras installed or observed, there would be an 11.59% chance that the sample mean for these 51 intersections installed would be less than 5. That's going to be the one. If population mean number of accidents per year is 5.1, is another 51 accidents. Okay. And then last one. Once again, it's going to be one of the paragraph ones. The population mean number of accidents per year at intersections with cameras installed is 5.1, and another 51 intersections with cameras installed or observed, then there would be a 1% chance that we would end up falsely concluding that the population mean number of accidents with cameras installed is less than 5.1. That's the one. Okay, because it talks about the less than instead of the equals to. All right, so those are really tricked up questions. I mean, these are the ones I've had the hardest time answering when I went through these. But I'm telling you, it's got to be one of the 2 paragraph ones, and you have a lot of tries, so you can, change it if you get it wrong. Okay, what questions on that one? All right. Let's do number 8 or 9. Let's do 9, because 9 works differently. It gives you the data this time. According to the Carnegie unit system, the recommended number of hours students should study per unit is 2. So mu equals 2. Are statistics student study hours more than the recommended numbers? So the statistics students study for more than 2. All right, you don't see anything about the population standard deviation, so we're going to use the t-test again. Let's check them. Okay, so now what I do is, because we have a set of data, is I need to enter that data. So where we enter data in our calculator, you go to stat, edit, and if you got some stuff up there like I do, you go up and then hit clear, enter, and it clears it away. And then we're just going to put that data in. So 1.6, 1.6, 0.5, 0.9, 2.2, 3.6, 3.8, 3.8, 0.7, 4.4, and 1.5. So I put those in, and now I have my data in there. And so here's how we use that data to calculate the rest of the stuff. So we go into stat, tests down to t-test again. This time we're going to choose data. So we go over and highlight data. My mu is going to be 2. Mu 0 is going to be 2. And then my list is L1 for sure. List is L1 for sure. And then I'm going to go mu is greater than 2. So I'm hitting the greater than button. So greater than 2. And then calculate. So then I got my test statistic, T equals 0.555. My p-value is 0.2955. So my p-value, my level of significance is 0.01. 0.2955 is way bigger than 0.01. So bigger than. Therefore, we fail to reject. Remember, when the p is greater than alpha, you fail to reject. Let's solidify all these. So we got all those right. All right. So the data is not significantly, data suggests the population mean is not significantly more than 2 at 0.01. So there is sufficient evidence to conclude the population mean study time for statistics students is equal to 2. That's not going to be correct because it needs to talk about rejecting and stuff. So let's see what the second one says. The data suggests that the population mean study time per unit for statistics students is not significantly more than 2. So there's insufficient evidence to conclude that the population mean is more than 2. That's going to be the right one, hopefully. If it's not, I don't know what I'm doing. The p-value in the context of the study, the p-value is 29.55%. So it's one of the first two. The population mean study time for statistics students is 2, and you survey another 11 stat students, then there would be a 29.55% chance that the population mean study time per students would be greater than 2. Then the other one talks about 2.24. If the population mean study time for statistics is 2 and you survey another 11 stat students, there's a 29.55% chance that it's greater than 2.24. Well, they're talking about this X bar up here, 2.24, but really it's going to be that one, the first one, because we're talking about testing against that 2. Oh, I got it wrong. So therefore it's that one. 29.55% chance you're going to get a mean greater than 2.24. Last but not least, if the population mean study time per unit for stat students is 2 and you survey another 11 students, there's a 1% chance we would end up falsely concluding that the population mean time for statistics students is more than 2. And then if the population mean study time per unit for statistics students is more than 2, and if you survey another 11 stat students, there'd be a 1% chance we would end up falsely concluding that the population mean study time for statistics is equal to 2. It's the first one. Because they're talking about there's only a 1% chance. If you're out in that tail with the 1%, if your test stat is out in that tail with the 1%, you're going to get the p-value less than the 0.01, and therefore you would conclude that the mean study time is more than 2. So there's a 1% chance that you could falsely conclude that, according to this this hypothesis testing. So tricky. What questions y'all have before we go to the other section? Nothing. All right. Let's look at the other section, see how many more I can get wrong today. We're going to do this one. All right, so this one now we're testing against population proportions. So instead of a mean, we're looking at a percentage. Like for number one, you're conducting a study to see if the proportion of voters who prefer the Democratic candidate is significantly different from 75% at a level of significance of 0.05. According to your sample, 44 out of 60 potential voters prefer the Democratic candidate. 44 out of 60 is pretty stinking close to 75%. All of these, the first one's going to be z-test. We use the z-test for population proportion. All right, so the null, this time in this whole section, we're talking about the p, the sample proportion. So is p equal to 0.75, or is p different from it? It just says significantly different, or is p not equal to 0.75? So then the third stats test we use today is stat tests one prop z test. So one proportion z test. So our P0 is the 0.75, just comes from right there. And then your test statistic, well, let's see, we got to do that. And then your X value is going to be 44. And then your N value is 60. And then you're doing a does not equals. The alternate hypothesis is does not equals. All right, and then calculate. And your test statistic right there, Z equals negative 0.298. And then your P value is 0.7656. I told you 44 out of 60 was really close to 75%. The P value is definitely greater than alpha, right? Alpha is at 0.05. Let's make sure that those all take before we move on. Very good. All right, based on this, P is greater than alpha. It's always fail to reject. Fail to reject. Okay, so the data suggests the population proportion is not significantly different from 75% at 0.05. So there is not sufficient evidence to conclude that the proportion of voters who prefer the Democratic candidate is different from 0.75. All right, let's read the last one because we don't have significant. It's definitely not the second one because it says the data is significantly different. So this last one, data suggests that the population proportion is not significantly different from 75% at 0.05. So there's sufficient evidence to conclude that the proportion of voters who prefer the Democratic candidate is equal to 75%. We're talking about whether there is sufficient evidence or not to figure out if it's different. So I believe it's going to be the first dot. Oh, let's cross our fingers here. Okay. The p-value is 76.56%. One of the paragraphs is going to be correct. The sample proportion of voters who prefer the Democratic candidate is 74%. And if another 64 voters are surveyed, then there would be a 76.56% chance we could conclude either fewer than 75% of the voters or more than 75% of the voters prefer the Democratic candidate. Holy smokes, that's a lot of words. At the population proportion of voters who prefer the Democratic candidate is 75%. Okay, that's what we're trying to refute or accept the claim on, is that 75%. And if another 60 voters are surveyed, then there would be a 76.56% chance that either fewer than 74% or bigger than 76%. So I'm not sure where they're getting those numbers. It must be from the 0.73 here. So that's the one I'm going to choose. Okay, because we're trying to figure out something about the population proportion. So I'm not going to say this sample proportion. All right. Population proportion of voters who prefer Democratic candidate is 75%. Another 60 voters are surveyed. then there would be a 5% chance we would end up falsely concluding that the proportion of voters who prefer the Democratic candidate is different from 75%. Let's read the last one. If the proportion of voters who prefer the Democratic candidate is different from 75%, and if another 60 voters are surveyed, then there would be a 5% chance we would end up falsely concluding. Well, we're trying to prove it's going to be the first one. Okay, because the last one talks about falsely concluding that the proportion of voters is equal to 75%. Okay, we're trying to accept or reject or fail to reject the null hypothesis. It's got nothing to do with falsely concluding proportion of voters is equal to. We either accept it or not accept it, or reject it or fail to reject it. Okay. What questions on that one? All right, let's go and do number 3. So all 4 of these work the same. All 4 of them are basically the same problem with, number 4 is a little shorter, but we'll do number 3. 16% of all Americans suffer from sleep apnea. Researcher suspects that a lower percentage of those who live in the inner city have sleep apnea. Okay, so P equals 0.16. This one, P is lower than 0.16. The researcher suspects that a lower percentage of those who live in the inner city have sleep apnea. All right, so we're using the Z-test for population proportion again. All right, then we're going to go and put that in the calculator. Number 5. So we got a 0.16 for my P. I got an X of 47. I got an N of 365 because 47 out of 365 had sleep apnea. And I want to change this to a less than. Okay, now we calculate it. And we come up with a Z value of negative 1.628. And the P value is 0.0518. So the P value is definitely greater than the alpha value of 0.01. So based on this, we fail to reject, right? P is greater than, we fail to reject. Okay, let's check all those, make sure we didn't booger it up somewhere. Looking good. So the final conclusion. So the data suggests the population proportion is not significantly different. It's going to be or significantly smaller than 16% at 0.01. So there is sufficient evidence to conclude that the population proportion of inner city residents who have sleep apnea is equal to 16%. Let's read the second one and see how it differs. The data suggests the population proportion is not significantly smaller than 16% at 0.01, so there is not sufficient evidence to conclude the population proportion of inner city residents who have sleep apnea is smaller than 16%. That's the claim that the researcher made, that it is smaller. So we don't have that evidence to conclude that it is smaller. That's the one I'm going with. Cross your fingers, everybody. Looks like we're good. So interpret the p-value. If the sample proportion of inner city residents who have sleep apnea is 13%, and if another 365, there's the sample proportion is 13% in this one. So that's where that's coming from. And if another 365 inner city residents are surveyed, there would be a 5.18% chance, that's the p-value, that fewer than 16% of city residents have sleep apnea. Okay, let's read the next one. If the population proportion of inner city residents who have sleep apnea is 16%, and if another 365 inner city residents are surveyed, then there would be a 5.18% chance, that's the p-value, fewer than 13%. So that's your p hat. But that's talking about that is talking about, I'm gonna choose this one. Nope. It's this one. Okay, so we got to be talking about the population proportion with the p-value. Because that's what we're trying to figure out the thing about. So it doesn't matter to talk about sample proportion in that one. Then the last one, level of significance is 1%. So if the population of inner city residents who have sleep apnea is 16%, and if another 365 inner city residents are surveyed, then there would be a 1% chance that you would end up falsely concluded that the proportion is smaller than 16%. Second dot, if the population proportion of inner city residents who have sleep apnea is smaller than 16%, if another 365 inner city residents survey, there would be a 1% chance we would end up falsely concluding that the proportion of all inner city residents is equal to 16%. Gotta be that one. So 1% chance that you're gonna collect data that ends up having you falsely conclude that the proportion is smaller than 16. All right, so that's how to do these problems. Like I said, the background and more of the theory behind how all this stuff works, I would watch Wendy's videos, read the book. Apparently I need to read the book again so I can explain those how to do these word problems correctly. I gotta tell you, reason I didn't get into Yale, I applied to Yale. The reason I didn't get in is because I stink with words. I had terrible SAT verbal. There you go. Sharon's TMI, right? Too much info. All right, y'all have any questions on any of that stuff? I'm gonna stop recording here in a minute and then the four of us can look at some of yours if you want. All right. I am going to stop sharing. Stop recording.